Hi, this is day 3 of the 30 days challenge. Today I'm going to talk about heap sort. So, heap sort is a process of sorting the elements that you want to sort using the heaps. But before explaining the heap sort, I just want to revise the insertion and deletion in max heap. So, how do we insert in a max heap? In the max heap, we have the elements sorted. When we want to insert in a max heap, we insert at the last available space. This is the space that will be available, and it will, if we visualize in a tree, this is a max heap. So if we want to insert in a max heap, we will insert at the last leaf, last available element. Here it will get inserted, and then we will compare it with its parent. If the parent is smaller, then we stop the node until we reach the root node. So we go from bottom towards the root in a max heap while inserting, and in the while deletion, we delete the root node. This is a max heap, so we delete the root node, and then we place the last element from the heap in the root, and then we compare the root with its children and swap it if the root is smaller until we reach the leaf, until we get the max heap property. So that's how we go from top to bottom while deletion in a max heap. So there are two steps to sort elements using a heap sort. The first is we create the heap, and the second step is we delete all elements in that heap so that we get a sorted sequence. Another thing to observe is while if we keep deleting the elements from this max heap, suppose at this point we delete the 12. So if we store it somewhere, then comes the next element. Always the root element will be the largest element in a max heap. So if we keep getting the root element out of the max heap, then if we store that somewhere in an array, we get the elements in the sorted order. That's what is the idea behind heap sort. So the first step is we create the heap using the numbers that we want to sort, and we delete all the numbers and store it somewhere to get the sorted sequence. So these are the numbers that I want to sort. In the first step, suppose we have 10 in our heap. And just observe that I'm using array based on index 1. The index of the array starts from 1. And if the in this way, if the current element is at I, current node is I, then its left child will be at 2i. Suppose you take I as 1, then its left child will be 2, 1, 2. Then its right child will be 3. So if I just name this as 1, this will be 2, this will be 3. So that's how you get the array representation for arrays based on index 1. So for now, we have only one node in our heap, so that is sorted. Now let's insert 20 in the heap. We have 10 in our heap. Let's insert 20 in the next node. Now after inserting, we need to take care of the heap property, whether the heap property of our max heap satisfies or not. So we need to compare the inserted node with its parent. The inserted node is 20. Here, compare it with its parent, which is at index 1. So the parent node is smaller here. We need to swap them. Now the heap satisfies the heap property. So we have inserted 2 elements. Now let's move on to inserting 15. Our heap contains 20, 10, and then we are inserting 15 here. 20 is here, 10 is here. We are inserting 50 here. Now this is the node that we inserted, 15. We need to compare it with its parent. Its parent, if the node is at 3, here as you see, if the node is at index I, then its parent is at index I by 2, floor value of I by 2. So in this case, it will be at index 1. Compare 15 and 20. Here, if you see, compare 15 node with its parent. So the parent node is greater, no need to swap in this case. We have the heap with 3 elements, 20, 10, and 15. 20, 10, and 50. This is the array of numbers that we are trying to solve. We have placed 10, 20, and 15 in the heap. That is our heap. Now we need to insert 30. 20, 10, 15. So we insert at the next space that is available. We have 30 here. This is how we fill. First we created a root node, then we went on to the next level. We fill it from left to right, then come to the next level, fill it from left to right. So the 30 comes here. Now after 30 is inserted, we need to compare it with its parent. 4 by 2 is 2. So at 2 index, we have 10. 10 is smaller. The parent node is smaller. So in this case, we need to swap 10 and 30. The array also swap 10 and 30. Now we have 30. Again, the index is 2. By 2 we need to do to get the parent node. In this case, it is 1. So in this case also, parent is smaller. So swap the nodes. 30 comes here, 20 comes here, 30, 20. So this heap now satisfies the heap property of a max heap. Same we have 30, 20, 15, 10. The next element is 40. So we insert 40 in the next available place. Times the next available space is 40. So insert it there. Here, then the index of 40 is 5. 5 by 2 is the floor value is 2. So compare 40 with its parent. Parent node is smaller. So swap it 40 and 20. Here comes 40. Here goes 20. Now again compare. Now the 40 is at index 2. So 2 by 2 is 1. 1 is the parent node. Parent node is at index 1. So compare the values. Parent node is smaller. Swap it. That's how we created a heap using the elements that we want to sort. The time complexity of this, the time it takes to, we are inserting n elements, and to insert each element, it takes log n time, as it depends on the number of swaps and the height of the binary tree, height of the complete binary tree. Number of swaps that we want to do depends on the height of the complete binary tree. So at this point, we have created a heap. Now what we need to do is we need to, so here 40 and 30. Now let's just check 40 is greater than all its children. 30 is greater than its children. So this heap satisfies the massive property. The second step of heap sort is to delete all the nodes to get the elements in sorted order. This is the heap that we have after our first step. Now what we want to do, we want to keep deleting the root node until we get the elements. So in this case, the root node is 40. So we will delete 40 from the heap max heap, and we will need to place the last leaf element from our complete binary tree. So 40 is removed, 20 will come here. If we remove 40 from this array, the last element is 20, so that will come there. 30 remains here, 15 remains here, 10 remains here, and 20 is removed from this tree because we need to remove one, and this is gone in place of the root node. Now we will compare the children of the root node. In our case, that is 13 and 15. Whichever is greater, we compare it with the root. And if the root is smaller, we need to sort. So in this case, 30 comes here and 20 here. And then we again look at the node 20 and we see its children. If the children are greater, then we need to swap it. But here 10 is smaller than 20, we need to swap. At the end, we have 30, 20, 50, and 10. So we deleted one element from our heap, and now the heap is until here. This is where our heap ends now. This is the extra space that we have in our array. So we can utilize this space to store or place the element that we removed. Here we removed this 40. So let's here I want to place 40 here. Is placed here. Let's move on to the next step. In the next step again, we will be removing this 30. And in place of, we will be removing the first element from the array, that is 30. And in place of that, we will place the last element. 10 comes in place of 30. Here, 30 is removed. 10 comes here. 20 and 15 remains as this. 20 and 15. And 15. Now we have replaced the root with the last element of our heap, and the node that we deleted is 30. So we will be needing this, we will need this node to store in our available array. Here 40 was there in this is 40, and here this was our heap. This was our heap. So now 30 is we replace the root with the last leaf node. Compare its children first. 20 is greater. Compare 20 with its parent 30. Sorry. So we need to swap this. 20 comes here. 20 comes here and then comes here. So 20 and 10. 15 remains, and that's in place. Now this was the node that we deleted. So at this point, what happens? The heap is still here, and we can place this 30 in the next available space. Can place 30 in the this is space that is available to us. Our heap is still here. These three elements are inside our heap, and this was the available space that we are utilizing to store the elements that we are removing. Now, what elements do we have here? 20, 10, and 15. Here we have heap, and here we have our extra space. Now we will be removing the node 15 because we will remove next. We need to delete the next element, that is again the root. So after removing 20, we swap it with we place the last leaf in place of the root. So 15 comes here and 10 remains here, and 20 will be removed. 20 is removed from the heap. At the 20 is removed. So what we do now, after replacing the root node with the last leaf, we need to check if our heap satisfies the heap property. Compare it with the children. The parent is greater, so no need to swap here. No need to swap. Here comes 15 because 20 is removed. This is the empty space that we have in our heap. This is the heap that we have at this point. We have this empty space available, so we can store the deleted element 20 at this point. Now, again, we will be removing the root node from the heap. Remove the root node in place of it. Place the last element, last leaf. So we removed 15 from here. We placed our last leaf here, and the elements that we had in our available space were 20, 30, and 40. At this point, this is the heap that we had, and the root that we deleted placed at the extra available space. Now again, in the next step, we remove this 10, and there is nothing to swap it with. So we remove the 10 from here. It is removed from here, and it is what we just popped. Now we don't have this heap. This is not the heap that we have. So this was the available space. So we will place the popped root in heap. So now if you see the array, that is in sorted order. So the time that it takes to sort the elements, to delete all the elements from a heap is also big of n log n, as we are deleting all n elements, and it takes log n time to delete um, each element, and then to maintain its heap property and complete binary tree property. So for creating the heap, it took n log n time. Then for deleting all elements, it took n log n time. N log n plus n log n is 2n log n. The time complexity of heap sort is n log n. That's how the heap sort works. Then I also want to talk about the Heapify. Heapify is also a process of creating a heap, but we saw this creation of heap. This is different from Heapify. How means um, while creating the heap, we insert at the bottom at the last position that is available, and we compare it with its parent to swap to maintain the heap property. We do this until we reach the node. So we are going from bottom to top. In the heapify process, we take a node and we look at its descendants. If its descendants and this node maintains the heapify property or not. If it doesn't, we just shuffle and maintain its heap property, and then we go up to the next element. So in the in this in this creation of heap, we go from left to right of the array. But in the heapify process, we create a heap from right to left. So the last element in our array is 18. So this is the node 18. Look at this node. This is the leaf node, so it doesn't have any descendants. So this is sorted. This heap is sorted. Then look at the next element in our array, that is 15. This node also does not have any descendants, so this is sorted in itself. Again, go to the next 40. Here, 40 should be there. 40. Look at its descendants. It's no descendants, so it's sorted. Go to 12. No descendants, it's sorted. Then we were here, 12. Now the next element is 25. Now ignore all the other elements, just look at this 25 and its descendants. Check if this is a binary tree. So check if this tree is a max heap or not. Compare its children first. 18 is greater, so compare 18 with 25. Here 25 is greater, no need to swap. So this 25, 15 and 18 is a sorted heap. Now go to the next element, which is 20. And 20, look at its descendants, compare its children. 40 is greater. Now compare 40 with the 20. We need to swap here. 40 comes 20, 40 and 20. So now we move on to the next element, that is 10, which is also root node. If you look at the root node, that is the only unsorted element in our heap. Its subtrees are sorted at this point. They are all sorted heaps at this point. So just look at this root node, compare its children 40 and 25, whichever is greater. Compare that with the root node. In this case, we need to swap. So 40 comes there, 10 comes here, 40 and 10. Yeah. So this is another way to create a heap. This is not a way to sort. This is just the first step of our heap sort. There are two ways that I have shown. One was we were inserting at the bottom and then we were looking up to maintain the heap property. In the Heapify process, we were looking at a node and we're looking at its descendants. So from top, we were looking down. This is another way of creating a heap, which is called Heapify. So Heapify takes big O of n uh, time complexity to create a heap, while that way of creating a heap takes n log n. So the minimum time taken for creating a heap is being often, which is using the Heapify process. That's it. That's all. Thanks.